Yeah, that's my name. We're going to do algebra part of this topic together. 24 lectures. I hope you will enjoy them. There are a lot of interesting and exciting stuff we're going to discuss. Because it's my first, because it's your first lecture in this topic, I have to discuss with you a little bit of the administrative stuff. The lecture which will follow, which is a calculus lecture, it will take off straight away from calculus, but I need to discuss a little bit with you the administrative part of this topic. So I'll take you straight to Moodle. That will be my and the other lecturer main channel of communication with you, Moodle. It's here. I just pre-opened the page for us. That's our area on Moodle. Two things I'd like to show you on this Moodle before we move on with the algebra material. Yesterday I spent a few hours organizing my section of Moodle. This is here. It's algebra component. In fact, I have already uploaded quite a substantial amount of the information from 2014. You can see all of it here. Basically, the thing which in my opinion, which will. Thank you very much. Like I said, it's a huge class. It's hard to control everyone. And everyone is late, or many of you late. Don't worry about the boxes or books. You will take them in the break between the lectures. It's not really of great importance right now. So I spent a few hours yesterday trying to organize these things. I left open all of the material which I put together in 2014. You can find it here, you see, 2014 lecture set. All of the lectures I delivered 12 months ago to the similar class like yours. They're all available. I'm not hiding it from you. You can look for them. Not only the lectures, there are also video recordings of almost every lecture there, split in parts. So you're free to browse through them. I'll revisit all of this material here. I will revisit some of it. Some of it I will leave for you to look through. I will probably introduce some new parts, but like I said, everything is available. You can look through it and you can enjoy it. Not only that, I also made a special section here yesterday which I call Tutorial Problems with Solutions. 12 months ago when I was doing this topic, we solved quite a few problems here in class with a similar lot like yours. And all of those solutions I kept recorded, both printed versions and video recordings of those demonstrations in class. They all here, all of that, they're not all here yet. It's only those which are in connection with chapter 6 I put together, just because I didn't have enough time yesterday to make the rest of the chapters. As we go through, I'll put the rest of the chapters as well. There will be chapter 7, 8, 9, and 10. All of the chapters and tutorial-related questions to those chapters we've done, or we did 12 months ago. They will be here, and you can use them freely for your reference, for your help. All you can do, I do everything to ensure you successfully get through this topic. Right. Another good thing which you can benefit from is the index. It's a very powerful thing, which I call concept index. You see, it's here. It's the first position in this section on algebra component. If you forgot something, like you forgot what's the definition of one concept is, or what was the exact statement of a theorem we discussed is, you can try to find it here in a concept index. It's already quite big index. Again, I put this index together in 2014. As we go together this year, I will improve the index, I will expand the index, I will fix the typos and errors in the index. If you spot something wrong with the index or with anything else for that matter, let me know. I will make the alterations, I will make the fixing and everything else. It's quite a big index, you see. Everything we discussed 12 months ago, it's available to you. You can use the index. And like I said, I'm not hiding anything from you. That's right. Now, we're still discussing administrative stuff. A few things I have to discuss with you about the topic in general, not specifically about the algebra part. First, I need to show you the page which the first year office asked me to show you. You can find this page. The last link here, The last link here in the algebra component, I called it the complete set of the material. It's basically just a collection of all of this together on the web page. You can go through this as well. It opens the table of content, which is quite big, and basically that's the content from 2014. That's why I just split it separate. Anyway, the first link here, which is called the, oops. It looks like it's, oh, sick. Well, I'll tell you what's happening. My web browser somehow shows me the old version of the page. That's why the link is, well, it's actually here, administrative matters. In fact, on the new page, the link is the first in the list, but it's not really relevant. That's the page which I need to show you. That's the page which the first year office asked me to show you. Yeah, here it is. It's some sort of administrative information about this topic which you need to know. I'll take you quickly through this page. Right, so the first thing you have to keep in mind is that there are some exclusions to this topic. They are listed here, all of the exclusions. If you have done one of those topics, you're not supposed to be here. I mean, eventually you will be, sorry for this, kicked out, but if you do it on your own, it will be probably easier for you. You won't waste your time and nerves and the rest of you. The web address of the school, I don't know how much interesting is that for you, but just for your information, it's here on this page. The link to the Moodle page, this one I'm sure you know very well. Official university email address. This is something you probably was told a few times already. I just repeat it again. When we communicate with you, send you the announcements, important dates, your results, we normally send this to your university email address. So it is highly encouraged that you change this, that you check this university address on a regular basis. Prerequisites, it's another thing which you need to keep in mind. The prerequisite for this course is the pass, even conceded pass for Math 1151. If you don't have that, you're not supposed to be here. You will be unenrolled from this topic if you don't meet this criteria. Tutorials, they will start next week. You will have altogether 13 tutorials once a week. You will be split into groups. You are split already into groups. You need to know your tutorial. Nobody stops you from coming to another, not the tutorial you officially enrolled into. But one thing you have to keep in mind, when it comes to tests, you're supposed to see the test in the tutorial you're officially enrolled to. If you come to some other tutorial, even if you by miracle will be able to write a test paper, it's highly unlikely your test will not be properly marked. So you're supposed to be in the tutorial group you enrolled to when it comes to class tests. Otherwise, there is some flexibility. Course specs, it's a big bundle of books. Well, these red books, they are the part of that bundle, but because of some delays with the printing services, these books have not been included in the course spec. That's why you are given them here. But the rest of the bundle, including the part which is linked to algebra, to my part, it's a thick yellow book. They are available for the bookshop, and I expect you to have this yellow book. This yellow book, it has two parts. It has a reference part, basically like a textbook, and there's a question part, tutorial questions part. That's the part which I'm going to refer to very often. Those tutorial questions I showed you before on Moodle, they refer to this yellow book. Textbooks, students might wish to delay buying the calculus textbook for a week or so. I don't know the meaning of this sentence. I just show it to you and you enjoy it. Any questions? Now, the last bit referring to the administrative part is what is called the course handout. It's another PDF document which you can find on Moodle. This is another one which you need to read very carefully, especially in the part which refers to assessment. It's a 32 or something page long document, sorry. That's a table of content of this document. This section on assessment should be particularly interesting to you. Computing tests, schedule of all class assessments, all of these sections you have to at least briefly look through. Page 3 is the assessments in this topic. Algebra calculus class tests, those which you're supposed to be in the tutorials you enrolled to. Online algebra calculus tests and the weighings of each of the tests in your final mark. All of this here. Yeah, it's schedules of the assessments, everything is here. So, like I said, I strongly encourage you to have a look through this document and know at least the basics of what's happening and when it is happening. Okie dokie. Any questions? Yes. Probability. Are we going to study probability? I don't think I have probability in the algebra part, and I don't think there is any probability in the calculus. I don't think so. No. Are you afraid so much of probability? Are you afraid so much of a probability? You just hate it, eh? Okay. All right. You're gonna die in this class. Okay, can I please steal your attention? Hello? Hello? Thank you very much. I know it's a difficult lecture. It's only the first one of it, so it's already a difficult one, especially because it starts at 4 p.m. But you willingly chose this class, right? That's right. Normally, when we start, our first chapter, it's about complex numbers. And normally when we start discussing complex numbers, we try to put them into perspective where they are in relation to the other types of numbers we know. And that's the first slide I normally discuss when we discuss complex numbers. That's a slide which I call number systems. So far, if you put all of the numbers you know in sort of like a regular systematic table, you will see something like this. We will do it rather quickly, so there's no point just doing it like a step by step. You will see something like this. You have these 5 canonical classes of numbers, 4 of which you know, at least you think you are an expert with them. With the complex numbers, I presume some of you think that they are also close to be classified like an expert. I'm fine with this, but this slide does, it just gives you this systematic look at these classes of numbers. So the smallest class of numbers you know is what is called the positive integers, or sometimes people call them the natural numbers. That's why in particular they use the capital N to denote that class. Integers, which include the negative integers and 0. Rationals, which basically the quotients of integers, of 2 integers, given that the denominator is non-zero. Real numbers is getting a bit tricky, because if I ask anyone here what's the real number, I highly suspect no one will be able to tell me what that is, even though you think you're an expert in the real number, isn't it? What's the real number? Oops. You don't have to answer. Probably you don't know the answer. Surprise, surprise. Does anyone know the answer? What's the real number? Yes, please.
A number you can represent.
I can take that. I can take that. Yeah, well, that's probably the most visual way to tell what the numbers are, even though it's a very slippery definition. yeah, we can think of numbers, we can think of them like so. It's hardly classifies for a definition, qualifies for a definition, but we can think of them as points on a real line or on a real line, and that helps. That helps a lot. Right. Now, a few questions in the yellow book, they concern classes of numbers, and they concern them from the perspective of which classes are closed and which classes are not closed with respect to a particular set of operations on numbers. And I'll make this quick demonstration what they mean when they discuss this. It's on this side of a slide. Yeah, wait a second. Yeah. Here it is. That's a table which explains what people mean when they say closed or not closed with respect to a set of operations. Look at this. So when someone tells you whether, say, a set of natural numbers or a set of positive integers is not closed with respect to addition, and this statement is encoded by this, actually is closed. I said not closed, which is wrong. It is closed with respect to addition, and this statement is encoded in this letter Y here. What's happening today? I'm sorry. In this letter Y here, in this one, it means that if you take two positive integers and if you add them up, the result will be again a positive integer. Quite similar effect will be if you, rather than adding them up, you will multiply them. If you multiply two positive integers, the result will be another positive integer, and that's another evidence, which let's say an evidence which supports the statement that the class of positive integers is closed under operation of multiplication, and that's another Y here which encodes that. If you move down the set of operations which we know with like a first regular set of operations, if you take the operation of taking negative number in relation to class of positive integers, this is no longer closed. I mean, the class of positive integers is no longer closed with respect to operation of taking negative over number. Because if you take a positive integer, say 2, the negative of 2 will be negative 2, which is no longer positive integer. That's all there is to it, to this idea of set of numbers being closed under some operation. And this table actually shows you the relation between 4 standard operations: addition, multiplication, taking negative, taking the inverse, and 5 classes of numbers. I included the complex numbers here as well, even though we formally speaking we did not discuss what are the operations on complex numbers yet. But I included them because for all of the operations we will have there, the answer will be yes all the time. There are a few questions in the yellow book, in the tutorial book, which actually play around this idea of set of numbers being closed or not being closed with respect to a set of operations. I have a few examples ready to discuss with you today, and yeah, well, you will get a feeling of this idea even more with those examples. Right. The other interesting way you can think of the relations between different classes of numbers is the solvability of equations. It's another table which is on the slide. It's another table which I will open relatively quickly because it's just a table to think about. Here, just here's a table. It's another table which shows you some relations between the classes of numbers. This time I just compare them in terms of which equations are solvable and which equations are not solvable over a particular set of numbers. So that's the simplest equation there is. X take 2 equals 0. We all know what's the solution to that equation, right? It's x equal 2, right? And because 2 is a positive integer, by implication it is an integer, by implication it is a rational, by implication it is a real number, and by implication it will be complex when it comes to it. it means that my first chosen, this equation, x take 2, it is solvable across all of the 5 canonical classes of numbers. If I take another example now, say x plus 2, the picture will be slightly different now, because this equation, even though we all know what the solution is, right, it's negative 2 this time. This time, it is no longer solvable within the smallest class, the class of positive integers. We need to extend the class a little bit in order to accommodate the solution. We need to take the integers all together to accommodate the solution, and only over that class it will be solvable. The next equation, and actually this reflects the way the the numbers were progressed through the history. I mean, one of the what the heck? I'm sorry. One of the motivations for introducing larger and larger classes of numbers was the inability to solve the existing equations within the existing class of numbers. If, like with the integers, it's like nobody knows when exactly that happened, because the integers were known even probably in prehistoric times. With the rationals, we more or less certain when exactly the need for that appeared, right? So if you take the equation like so, if you facing a need to solve an equation like that, and if you're only aware of 2 classes of numbers, integers and positive integers and integers, you won't be able to solve this equation. In order to be able to solve this equation, you need to introduce this larger class, which we now know and which we now call rationals. So next time when the humanity moved through the history and they faced another type of equation, like a quadratic equation, they realized that the rationals are no longer sufficient to accommodate the solution to this equation. That's why the need appeared to introduce a larger class, the class which we now call real numbers. In a similar fashion, when they realize that the real numbers are not enough, then they do not suffice to accommodate the solution to the equation like so, x squared plus 1 equal 1, the need came to introduce a larger class, which is complex numbers, within which we can solve this equation. You will see this quite soon. The interesting thing, though, now comes back, like if you look at these 5 equations, we were like making up new equations which we couldn't solve in the existing class. We introduce a newer class. If you try to do the same exercise with the complex numbers, if you try to think up an equation which cannot be solved in complex numbers, and people try hard actually to think of such equation in order to, just to show that we need to invent some larger class, it turns out you can't. Within complex numbers, every equation will be solvable. This is something which was discovered by, when mathematicians were just developing these equations and solutions to equations and extending the class of numbers, they were thinking that eventually they will hit this brick wall beyond which you don't have to go. But they did, and that was quite a discovery. It's a discovery which is called the fundamental theorem of algebra. We will discuss it with you in the due course. But even now you can appreciate the depth of this result. Complex numbers are so universal, are so fundamental, you don't need to go anywhere else. Any equation is solvable there. You can't really think of an equation, no matter how hard you will try, which won't be solvable within the complex numbers. Any questions? Okay. A few last comments in relation to this slide. These 5 classes of numbers, canonical I call them, they are not all classes there is. There are many other classes you can think of. You can take like any finite set of numbers. But with the finite set of numbers, as we will see, actually, it's a 3rd question in the tutorial book, the question number 3. It shows that with the finite set of numbers, especially when you discuss this question of which of them are closed, which of them are not closed, the answers are quite boring. But beside the finite set of numbers, there are many other classes of numbers which are also show some closedness with respect to plus or times or taking the inverse or taking the negatives. There are plenty of such classes. In fact, I can ask you, can you come up with any example of a set of numbers, or a class of numbers, which are closed under, say, addition, and which are not one of these 5? Or let me just put it like that. Can you think of a simplest possible class of numbers, or set of numbers, which is closed under addition? 0? Is that the simplest? Well, actually, 0 is not a class of numbers. You want to say a set consisting of a 0. Is that right? Is that what you're saying? I'm sorry, it was you. I'm sorry. Oh, thank you very much. The empty set, of course, empty set is the simplest one, even though it has nothing to do with numbers, right? It's like a universal set which has to do with everything or with nothing. It depends on your, attitude. That's right. The empty set is the simplest one. It's closed under addition. You can't deny that. If I take 2 elements of an empty set, if I add them, it will be an empty set. It will be in the empty set. What's wrong with that? The set which consists of just one number 0, it's also a good example. If you take 2 elements from a set consisting of a 0, you will end up with 2 zeros. If you add them, you will end up with 0 again, so it's also closed. Any other examples? Do you know any other? Can you come up with any other example of a set which is closed with respect to addition, beside these 5 and beside these 2 rather trivial examples we just discovered? Any? Quaternions? What's the quaternions? No, I don't know that. It's too scary. Something simpler, please. Quaternions. Are you sure you're on the right topic? Okay. No. I mean within the real numbers. Within the integers. Within the integers, please. We don't have to go this high universes, quaternions. Just within the integers. Do we have any other sets which closed under addition? No. That's a very boring picture. Are you sure? Not at all. Yes, please. Thank you very much. The set of even numbers. If you add 2 even numbers, it will be an even number. If you take a negative 2 in even number, it will be an even number. If you multiply 2 even numbers, it will be another even number. Well, so in fact, even numbers will have this. If I put even numbers into this table, it will have the same column as this one: three y's, 3 yeses, and 1 no. Inverses, of course, they don't work with even numbers. The inverse of an even number is no longer an even integer number. Any other examples? Even numbers give us some ideas, no? Don't they? You can develop these ideas and say...
You can extend that to multiples of 3 and multiples of 4, etc.
You can take multiples of any other integer. That's right. Thank you very much. You can take multiples of 3. That will be the same picture as with even numbers, multiple of 4. So even this example shows, even within this quite restrictive set of integers, you can find sets which are closed with respect to addition, multiplication, and taking the negative, and which are different from the integers themselves. That just shows you, I hope it shows you, that the classes of numbers which are closed with respect to operations, some of them or all of them, they're quite diverse. On this slide, I have this example, and that can be a good challenge to you. If you take the class like this, so you see it's a class of numbers. It is within real numbers. It's a class of numbers which consists of a particular type of combinations. You see, you take 2 rationals, you add them up, and one of them you scale with the root 2. You can think of it as a challenge or like a task if you have spare time on a train trip home or something. You can think about that. This class, interestingly enough, it will be closed with respect to all of the operations here. If you add 2 numbers of this type together, it will be a number of this type. if you multiply two numbers of this type together, it will be a number of this type. If you take the negative, it will be a number of this type. The first three are not so hard, actually. But the interesting thing is, if you take the quotient, the inverse of a number of this type, that's the hardest part of all, it will be, again, a number of this type. I wonder if you can discover why. But this is true. In fact, this one, this set of numbers, it will be the one which is very, very similar to real numbers, or, I mean, it will have all four y's here in this column. That's a good example. Any questions? Like I said, I have two examples from the yellow book which play around the idea of being closed or not being closed. Yeah. We'll just look into those two examples. So question 2 and question 3. I call it question 2 plus because actually I changed the question a little bit. So the question goes like this. The question goes like this: Is the set consisting of 5 numbers, 1, 2, 3, 4, 0, 1, 2, 3, 4? If is the set of these 5 numbers is closed under 4 operations we just discussed: addition, multiplication, taking the inverse, taking the negative, and taking the inverse operation. I said it 2 plus because it's a little bit different from the actual question in the yellow book. In the yellow book, if I remember correctly, there is a set of 9 numbers from 9 to 9. I changed it to 4 for a reason. You'll see the reason in a second. Right. So the question itself, it's not a hard question. The answer will be what the answer will be. For instance, plus. How would you answer what would be the answer to the first part of this question? Is this set closed under addition? What do you think? No. How would you convince someone that it is not closed? How would you convince someone? What would you do? You provide an example, right? You choose 2 numbers. You say 4 plus 3. I'm fine with this. Even though on my slide I said 2 and 4, but I'm fine with this. You want 4 plus 3. Let's just go. Not 33. That's bad. Okay. I'm sorry, it's just... Oh, I need to do something, I'm sorry. This is interesting. I need to reload this, I'm sorry. What the heck just happened? Yeah, I'm happy with 3. If you want a 3, why not? You can take 3 and 4, which are from the set. If you add them up, even though my original example was 2, if you add them up, it will be 7, which is not in a set, and that's as good as an example. The similar example, similar easy example you can come up in relation to, say, multiplication, right? You can take the same 3 and 4, or you can take, say, my original choice, 2 and 3. 2 numbers, they come from a set. If you multiply them, which is 6, it's no longer from the set. As easy as this. When you disprove something, all you have to do, you have to provide an example. You don't have to say many words. You don't have to write paragraphs of explanations. Nothing. Just one single example kills every hope for success. Right. Well, you can come up with similar examples for taking the negative. You can come up with a similar example for taking the inverse. And that's the end of it in relation to the original statement of the question number 2. Now, I call this question 2 plus for a reason, and the reason is this. I want to show you using this example. I want to show you how sometimes mathematicians invent new things in order to make things work. So what I'm going to do now is this. Well, what I realized together with you right now is that this set of numbers from 0 to 4, in relation to the canonical or standard operations, is very boring set. It's not close on the plus, it's not close on the times, it's not close on the taking negative, it's not close on the taking the inverse. It's a boring set of operations. What I would like to do, I would like to introduce new set of operations. And interestingly enough, I can come up with the operations which resemble a lot plus times taking the inverse, taking the negative, with respect to which this set will become closed one. Look at this. It's a section which I called what if. So here the answer are, it's a section which I called what if. What if I introduce new plus operation? You see, I just gave a new symbol to this plus operation. I call it plus in a circle, or O plus. And this time, I'm no longer adding in a regular fashion. No, I don't. Instead, I plus the numbers, like before, but then I take this mod thing. Who knows what the mod thing is? Do you know this notation mod? Remainder, that's right. This is just it's a way to write that I add two numbers, and then I take the remainder with respect to number 5. For instance, if you look back at this example, 3 plus 7, if I need to compute 3 or plus 7, 3 or plus 7, what that will be? First I do 3 plus 7 as usual. Oh, sorry, not 7, my fault. 4. First I do 3 plus 4 as usual, right, which is 7. We all know that, right? No objections to 7 right now, isn't it? But then I have to take the remainder with respect to 5. What's the remainder with respect to 5? Of 7. Number 7, remainder 5. Number 7 mod 5, what is it? What is 7 mod 5? What's the remainder of 7 with respect to 5? Hey? Who said 2? Anyone said 2? Are you sure? Absolutely? 100%? Thank you. It's 2. And you can't deny 2 is within my set, isn't it? Number 2 is within my set. So even though original plus doesn't work, doesn't make my S closed, my new plus does. And in fact, because my set is finite, I can just build the whole addition table, isn't it? I can take all possible pairs from my set 0, 0, 1, 0, 1, 0, 2, 0, 3, 0, 4, 1, 2, 1, 3, 1, 4. All of this, I can take all of these pairs. I can do the same sort of operation for this pairs, and it can come up with this addition table, new addition table, all plus addition table. Here it is. Here it is. I went the length and I built up this table. In fact, computing-wise, because in this topic you have a few computing type of assessments, it will be interesting if you will be able to devise a little algorithm within, what do we do, Maple or MATLAB? MATLAB. If you can devise a little algorithm within MATLAB or Maple, I don't care as a matter of fact, which can reproduce a similar table. But I did so, I made a table. That's the addition table for my new addition. And look at this. If you look for the results of this table, all of them within from my S set. So with my new operation, my set S is closed with respect to this new plus. If I do a similar trick, for times, if I do a similar trick for multiplication, if I introduce new type of multiplication, the O times, with the same idea behind it, I multiply first like numbers, and then I take the remainder with respect to number 5, and the same thing will be seen. I mean, my set will be closed with respect to this new multiplication operation. I can fill in this table, multiplication table. All of the results in this table will be from my set. But it's actually that's not a surprise, isn't it? Because when you take a remainder is supposed to be between 0 and 4. It's not a surprise that when you take a remainder, the things come back to the set from 0 to 4. So the fact that for the first two operations here, so look at this. We have all no answers for the canonical plus and times. We now have yes and yes answers for the first two operations. When I mean this, not these two, but the replacement operations. We have an yes and yes, and it's not. If you think about it just a little bit, you will realize it's not surprising, because when you take the remainder, you will end up with a number between 0 and 4. What's more surprising is, and that's something quite deep in mathematics, as a matter of fact, that if you now build these two derivative operations, because taking the negative or taking the inverse, they are not like a prime or primary operations. They are derivatives. They come as a consequence of the addition and multiplication. For instance, the negative number is the one which you add to the original, end up with 0. That's how you define the negative. And the inverse is the one is such a number which you multiply by the original and end up with the unity. That's how you define the inverse. So the other two operations, they are not independent. They are derivative from the first two. The interesting thing is, with respect to these two derivatives, the set S will also be closed. Look at this. Look at this. Look at these tables again. What if I ask you to find me the inverse of 2, negative 2? Is it within the set S? Yes, no? Well, the answer is yes. Because inverse of 2 is equal 3. What did you just said? No? You don't believe me? Now listen again to what I just said. What's the inverse? Sorry, I said inverse. My apologies. I meant the negative. What's the negative? The negative, by definition, it's the number which you add to the original and end up with 0, isn't it? If you take the negative of 2 must be the number which, if you add to 2, you end up with 0, right? That's what the negative is. But this time you add differently, right? This time you add not plus. You add O plus. So what number should I add to 2 in O plus sense to end up with 0? Look at this. Number 2. I'll look for the results. 0 happens here. I need to add 3 to that. If I add 3 to 2 in my O plus sense, it will be 0. Isn't it? So my set of finite numbers with respect to my new set of operations and negative of that is closed. The similar picture happens with the actual inverse now. Now I'm not misspeaking. The inverse, for instance, you can now see that the 1/2 equals 3. Because for the same reason, what's the 1/2? 1/2 is the one which you multiply by 2 and end up with 1. That's the definition of being 1/2. There's no any other definition of being 1/2. But this time you no longer do regular times. You do this times. Now take a number 2 from this multiplication table. Look for the results. 1 appears here. So you need to multiply 2 by 3 to end up with 1, which means 1/2 is 3, isn't it? If you just listen to this sentence without like listening what I said before, if I say 1/2 is 3, you say what a heresy he just said, isn't it? But in fact it is. 1/2 is 2. And my set is closed under my new multiplication. Any questions? What the heck? Okie dokie. I can see that you're very excited. And that's very good. It is a very advanced example, as a matter of fact. It is an advanced example. I cannot promise that you will, and probably it's a good thing, I cannot promise that you will see many of such examples in the yellow book. They are advanced examples, and maybe they are a little bit out of reach for your level, but it's a good example. There will be other examples on the question of being closed or not being closed. Some of them I'll show you. I mean, for some of them I have recordings already in the set I showed you on Moodle. The others you will do in the tutorial set, but I think that's enough for the first lecture at 4 p.m. on Tuesday. So thank you very much. It's a good point to stop. Good. Thank you. Maybe a break.